This is about input to state stability in nonlinear optimization algorithms, and in particular, input to state stability as, well, an instance of system theory when we look into optimization algorithms. So this is really in the intersection of systems theory on the one hand side and optimization on the other hand. And it's a continued joint work with Ilya Komanovsky from the University of Michigan Aerospace Engineering Department. Let's look at the basics. Optimization has, in my opinion, kind of two different views, and depending on how you view it, you see certain system dynamics popping up. So more classically, you would think of an optimization algorithm or an optimization problem as something that you have to solve once, and then you get the solution and you're happy with that. Example for that could be an interplanetary maneuver. You're computing some optimal trajectory for a space probe going to some faraway planet, and you want to optimize swing by maneuvers by other planets to kind of exploit as much gravity assist as possible. You would solve this optimization problem once, and then you pretty much apply the solution to the space probe when you launch it. So importantly, you don't think too much about how long does it take to solve your optimization problem and what's happening in between. On the contrary, and that's a kind of view in optimization that I want to discuss today, there are optimization problems that are solved repeatedly, even in some kind of feedback scheme. And that could be, for example, the navigation problem. You're solving the best route to get from one place to another. And then as you start driving, as you start following the route, you keep recomputing the best route, which also means that decisions that the driver takes on what the best route could be, and actually the driver following the recommendation or maybe not following the recommendation, affects future solutions to the same optimization problem. And actually the optimization problem is changing a little bit at every time instance because you've got other drivers' behavior, and of course you're progressing on the route. So in this latter view, optimization becomes something that we have to do repeatedly and possibly also in a somewhat fast manner. On the other hand, in that case, we might be less interested in getting the perfect, accurate, exact optimal solution. Maybe unlike the interplanetary maneuver, we really want to be sure that this is the best trajectory and that the trajectory is exact. But if we are driving, well, we probably don't mind if it takes a minute longer taking another route. Actually, the driver is never going to know anyway. So what starts happening is that optimization pops up in some kind of a feedback loop. And there are surprisingly many applications to this type of feedback loops. So just to somewhat explain this diagram, the architecture. So we have some kind of optimization problem in what is here at the lower level. It is parameterized in something that comes from an upper level. And then for each parameter, we are attempting to solve for an optimal solution. The optimal solution is fed back into the upper level, and the upper level makes a new decision, which then parameterizes a new instance of the same lower level optimization problem. And this happens in dynamical systems, where the lower level could be an optimal control problem that we solve for an MPC type control scheme. It could also be in a hyperparameter optimization in machine learning, or in some distributed optimization or bi-level optimization, where the upper level makes certain decisions centralizing multiple lower level optimization problems, and then solving the lower level optimization problems distributedly. Now, the question that I'm studying here, and where in a minute you see why input to state stability becomes relevant, is what's happening if the lower level optimization problem becomes perturbed or disturbed. So we have some exogenous signal that is affecting our lower level optimization problem. That could be some environmental disturbance, but it could actually also be real-time constraints. So we're solving the lower level inexactly because we don't have time to wait for an exact asymptotic solution. Now, once we have a disturbance in the lower level, that means that the optimal solution we are feeding back to the upper level possibly isn't optimal in an exact sense anymore. So we get an approximation of the optimal solution, which isn't the exact solution. So the upper level makes decision based on an approximate possible inaccurate solution. And the inaccuracy might be fed back through the parameterization of the lower level optimization problem. I prepared a few very high-level examples of this scheme. As I've mentioned, model predictive control is one of the instances where this comes into play, and where actually ISS has been used to study these type of interconnections. So we have an optimal control problem parameterized in the current initial state of our dynamic system. We solve for an optimal input trajectory. The input trajectory is applied, or actually the first value of it is applied to your dynamical system. Dynamical system evolves. You measure again the system state. System states then become a new parameter of your optimal control problem. In hyperparameter training, you would train a neural network, solve for optimal weights in your neural network based on a certain parameterization of the neural network. And then, depending on the optimal weights, you would try to improve the parameter. For example, you might want to optimize some cross-validation accuracy. Surprisingly, at least for me, when I first looked at it, this type of feedback optimization also pops up in other optimization algorithms. So augmented Lagrangian method is a very prominent example of that. You're solving the augmented Lagrangian for a given dual solution as a parameter to obtain a new primal solution as the optimal solution to the augmented Lagrangian. And then based on the new primal solution, you make an update of your dual solution. The dual update becomes the upper level decision unit that parameterizes the primal step as in optimizing the augmented Lagrangian. Now, the question we want to ask in all of these architectures, or actually in a more general case for all of these different use cases, what's happening if you have disturbance in the lower level? How is it affecting the interconnection of lower level optimization problem and upper level decision-making process? And is it possible that we can still guarantee certain asymptotic convergence properties of the this bilevel structure despite having disturbances, or make certain statements about asymptotic convergence if disturbance goes to zero, etc. I probably don't have to tell you in this seminar series that input to state stability is pretty much covering exactly these two questions of how is disturbance affecting my interconnected dynamics. Namely, we're going to say that a disturbed deterministic dynamic system is input to state stable if it is globally asymptotically stable under no disturbance, and it has an asymptotic gain property, meaning under the presence of disturbance, the asymptotic worst case disturbance, or worst case, what's it called? Worst case error in the system state is upper bounded by the largest value of the disturbance that we fit into the system. Which also means that if the disturbance goes to zero, eventually our system dynamics, our states are going to converge to zero too, or the error in the system state is going to converge. And one of the reasons we use ISS as a framework is that it has very nice properties when it comes to interconnections of systems. So if you have a feedback system, a feedback connection of two ISS systems, like the bilevel structure I showed you earlier, both of our levels are ISS themselves with certain gains, then the interconnection becomes ISS provided that a small gain condition is met. On the other hand, if we have a cascade, so we don't have a feedback connection of two ISS systems, then the cascade is always ISS. Now, we have been using ISS in the literature already when it comes to optimization loops. In particular, in the use case of MPC, some people have studied what's happening when you have finite number of iterations in the lower level optimization problem. So your disturbance becomes now the inaccuracy of the solution you have to feed back to your dynamic system. And we're able to show that even with a finite number of iterations sufficiently large, MPC feedback could asymptotically stable certain dynamic systems. We've applied similar ideas to bi-level optimization schemes where certain gradient-based algorithms were involved. And we could show that similarly, if you have inexact lower-level solutions, meaning you also get certain inaccuracies in the gradients that are used in the upper level, and you can still show asymptotic convergence. And you can even extend these results without assuming to the case where you have no differentiability in the lower level optimal value. So ISS has already been pretty useful in studying interconnections with optimization algorithms under the assumption that the underlying optimization algorithm was ISS in the first place. Which brings us to the question, which type of algorithms can be ISS and under which conditions would they be ISS? There's a fair body of literature on input-to-state stability properties of optimization algorithms, including some Newton-type method for equation systems, Q-linearly convergent algorithms, gradient descent and proximal gradient descent under some fairly strong assumptions, and recently by our work, Newton methods for generalized equations that I'm going to show later for optimization algorithms. But these include sequential quadratic programming and augmented Lagrangian methods. In the talk today, I want to go a little bit more into detail of the Giuseppe-Newton methods and discuss necessary and sufficient conditions for these type of optimization algorithms to be input-to-state stable. Before I really dive into these precise results, I want to give you a brief introduction into the tools we're going to use to build these results. The first tool is variational analysis. That's kind of the underlying concept, one of the underlying concepts in optimization. So if we are asking for a minimum, a local minimum of some continuously differentiable objective function over a closed and convex set of feasible solutions, then having a local minimum is equivalent to for any value or for any solution in the feasible set close to the local minimum, the objective function can at most be as large as at the minimum. That's pretty straightforward. And then we can actually consider a first order approximation of our objective function and have that in any feasible direction, our objective function or the first order approximation of the objective function must not decrease. Also pretty straightforward. If you had a feasible direction and your objective function decreases along the feasible direction, you cannot have a local minimum in the first place. Now this last condition, what we call a variational analysis, a variational inequality, is equivalent to, or we had equality that would be equivalent to being a search direction being tangential to our, not tangential, perpendicular to our feasible set. And this variational inequality pretty much means that our gradient of the objective function must be in the outward normal cone to the feasible set. Now, the normal cone depends on the current solution we are having. So it becomes a mapping from a primal solution into the dual space or to a set of dual variables, and we get what is called a generalized inequality or generalized equality because we are having now a set on the left-hand side. In particular, the full left-hand side of this generalized equality is in itself a set-valued mapping. So it takes sets as values for each given primal solution. And we can extend these ideas to more general Karush-Quinn-Tucker necessary conditions for optimization problems with equality and inequality constraints, so going beyond convex feasible sets. Then we also have dual variables. I'm going to show that later. And what's pretty much the takeaway here is that in nonlinear optimization, we often actually attempt to solve this generalized equation rather than the actual optimization problem. And that brings me to the idea of Newton methods. Now, of course, you're all aware of the classical Newton method to solve an equation system. You take a linearization and you use the linearization to update your solution. In Newton methods for optimization, we're doing something very similar. So we have an optimization problem like minimizing an objective function over a convex set. Now we have the necessary conditions in form of the generalized equation. And instead of solving these potentially nonlinear difficult problems, we are taking approximations. So we take some primal solution, we compute a second order approximation of our objective function, and the necessary conditions for the second order approximation of our objective function just happens to be the first order approximation of our generalized equation. So effectively, we have a connection from the approximate optimization problem to the necessary conditions, but also from the exact necessary conditions to the approximate necessary conditions. And now for these type of quadratic optimization problems, we usually know how to solve them. They're often just a quadratic program. So we can compute a new iterate as a solution to either the second order approximation of the optimization problem or equivalently, often equivalently, to the first order approximation of the generalized equation. And this now gives us effectively a dynamic system, although one which is defined by an inclusion, not by an equation anymore. So we're solving a generalized equation. The question, can a set-valued mapping contain 0 through some iteration defined by an inclusion? And we want to ask under which conditions on our generalized equation, our optimization problem, would this iteration be well defined and behave nicely in a systems theoretical sense, meaning it's going to converge, at least locally, to some optimizer. And if we perturb it, the inexact solution isn't going to divert or doing strange stuff. So we want certain nice behavior, and this nice behavior of our set-valued mapping, of our generalized equation, the inclusion system, in my talk at least, is characterized by the idea of regularity of a set-valued mapping. So different types of regularity. Going to speak mostly about strong regularity today. And these types of regularity can be thought of as some kind of surjectivity or injectivity in an operator. So an operator has a well-defined inverse or an open codomain. And in particular, if you have a linear operator, linear quadratic operator, then regularity is somewhat equivalent to this operator being non-singular. So an inverted compute the inverse as well defined. Again, different types of regularity have different meanings. I'm going to give you a proper mathematical definition later, but you can think of in this type of terms. It's important to note that the regularity is a local property. So we get some kind of local surjectivity, local injectivity, local invertibility, but it's also local in the sense of that if you have a perturbed problem, then these notions are stable under a perturbation. And that makes it very suitable to study the question of what's happening to perturbed optimization. So starting with a perturbation in our generalized equation, our necessary condition system, this perturbation would be propagated to our Newton type iteration. And if we have a certain notion of regularity at the unperturbed solution, we can actually infer that for small perturbations, the regularity is preserved, it's stable under the perturbation, meaning our optimization algorithm should still behave somewhat nicely. And this should still behave in the exact exact conditions under which this happens is what I'm going to talk about next. In particular, 3 different topics to discuss. The first is input to state stability properties of these Newton type optimization algorithms under strong regularity. The second then is a characterization of strong regularity in nonlinear programming problems, just to give you an idea of what this actually means in terms of more classical optimization notions. And the last, and I think for today the most interesting, is a system theoretical characterization of strong regularity. So it's pretty much the inverse. So in the beginning, we use strong regularity as a sufficient condition, and then we give a system theoretical necessary condition of strong regularity. Now, a little bit of a problem setup extending on what I've showed you before. The type of nonlinear optimization problem that I'm going to study is this type of inequality constrained optimization problem, where we have an equality constraint and an additional set of feasible solutions. Now, this does include inequality constraints if you basically add some slack variables, but I'm not explicitly studying inequality constraints in a classical sense, because then I have to deal with active constraints and stuff, and it's somewhat unpleasant. Most of my results extend to infinite dimensional spaces under certain conditions, but I'm not going to discuss a lot today. But just be noted that if you had an infinite dimensional space, you would need an Asplund space, and you need a certain sequential normal compactness property. If you have a finite dimensional space, which most people typically do optimization in, at least in a practical sense, then you don't have to worry about these things. We're always going to assume that we have a local optimal solution. That's pretty straightforward, because that's what we want to study around, and that our objective function and our constraint function are once continuously Fréchet differentiable around this optimal solution. Again, that's a fairly standard assumption if you want to do some gradient-based optimization. And for the sake of simplicity, we will assume that our feasible set is non-empty, closed, and convex. I think most of the results extend if you assume that it's only locally closed and convex. Well, it needs to be non-empty if you have an optimal solution in the first place. Now, under this assumption and some additional constraint qualifications, we get Karush Quintuple necessary conditions in the form of a generalized equation where we have a set-valued mapping in our primal and dual solution, set-valued because we have the normal cone to our feasible set included here. Otherwise, this is pretty much the standard necessary condition. So we have first-order gradient of our Lagrangian vanishes on the normal cone, is compensated by the normal cone in a sense. And of course, we have feasibility of our primal solution. Again, quick example, if you think of discrete time optimal control, in that case, your objective function is a sequence of typically quadratic stage costs. Or first of all, your primal solution typically is your predicted state trajectory and an input sequence. Your objective function is a sum of quadratic stage costs. Your equality constraints are typically that your predicted trajectory of states and input sequences satisfy a given discrete time dynamics. And your feasible set would be additional state and input constraints, typically given as polygonals or hyperboxes, so it can be represented as inequality constraints. And in such a discrete time optimal control problem, you would have a finite dimensional problem. Often you have twice differentiable objective function and constraints. I already said feasible set is given by linear constraints. I'm going to refer to this type of nonlinear program later when we study conditions under which strong regularity holds in this type of problems, because that's a question that is relatively well understood, whereas in the general case, it's a bit unclear when strong regularity is going to hold. Now, similar to the Newton methods I've shown you before for this convex optimization problem, we can apply a generalized Newton method to the generalized equation that is given by the KKT conditions, where we are computing an update of our now primal-dual solution based on an operator H, which is representing our Hessian of the Lagrangian, or an approximation of the Hessian of the Lagrangian if it doesn't exist, and then the normal cone mapping, which we extend to include the dual variable too. And there are a number of optimization approaches that we can get depending on the choice of the operator H. So in the ideal case where we have a Hessian and we use the exact Hessian here, we get sequential quadratic programming, where we have the gradients of our constraint function and the Hessian of the Lagrange function. If we omit the Hessian of the Lagrangian, or we omit the quadratic part altogether, we just use the first order approximation of our constraint, then we would get a sequential linear program. And we can even understand the type of projected gradient, although that doesn't really make sense in the primal-dual sense, but at least in the primal sense, the projected gradient is another instance of a generalized Newton method, where the Newton step actually becomes a projection onto the feasible set. Now, if we talk about perturbations, we have to talk about how is the perturbation entering our optimization problem. Here we are directly saying the perturbation is affecting our necessary conditions in the form that is affecting the left-hand side functional part, which is composed of the objective function and the constraint function. Actually, in the generalized equation, the necessary conditions, it's gradients. And then this perturbation is propagated into the Newton iteration as affecting our the evaluation of our functional bit, but also possibly the operator H that we use to approximate our generalized equation. Now we are going to say that a single-valued set-valued mapping, like the type we have in a generalized equation, is strongly regular at some primal-dual solution for the right-hand side value, typically 0, if and only if there exists neighborhoods of our primal-dual solution and the right-hand side on which the inverse of this operator is a single-valued Lipschitz continuous mapping, meaning that our set-valued mapping locally is invertible in a classical functional setting, and this inverse is Lipschitz continuous to the right-hand side, which then becomes a kind of canonical perturbation. That's actually equivalent, or strong regularity of this mapping is then equivalent to the inverse having the Lipschitz continuous single-valued localization. And this again is equivalent to having a single-valued mapping that is linearly open, so in a sense locally surjective and locally injective. So we have a unique, well-defined inverse. On the right-hand side graphic, we have the inverse of a square function, and this inverse is regular except at the origin. So at any value which is not the origin, we have a well-defined inverse. And that brings us to our first input to state stability result. Namely, if we have a solution to our generalized equation, primal-dual solution to our optimization problem, we have certain uniform Lipschitz continuity properties, meaning all the ingredients to our generalized equation are Lipschitz continuous in the arguments in a uniform sense. And in addition, our local approximation at the optimal solution is strongly regular with a given constant, where the regularity constant and the Lipschitz continuity constant have a gain condition. So the product is smaller than 1. That actually corresponds to having a sufficiently good approximation of our second order behavior by this operator H. Under these conditions, we can show that the iteration that is given by this type of generalized Newton method is locally unique. So the inclusion has exactly one solution and is locally input to state stable to small perturbations. The idea here is that by combining the Lipschitz continuity property with the strong regularity, we actually get a Lipschitz continuous single-valued localization of our solution mapping to the Newton's method. So the solutions of the inclusion, or next solution to the Newton's method, is unique and depends Lipschitz continuously on our current value of the primal-dual solution. And we can do inequalities of our distances using that an optimal solution is a fixed point to our Newton's method. We give in the optimal solution. There is the only unique solution to this second order, this first order approximation is the optimal solution again. And then by the small gain condition, we actually get a contractive algorithm. So the distance between the new iterate of the Newton's method and the previous iterate must get smaller. But if we have a perturbation in the system, that's where the input to state stability part comes into play. We have a perturbation, and this perturbation also affects the accuracy of our new iterate in a somewhat linear or Lipschitz continuous sense, classical input to state stability dissipativity condition. What we've used, as I said, is the combination of Lipschitz continuity and strong regularity in what is known in the literature on variation analysis as an implicit function theorem, or actually a generalized implicit function theorem, namely for a generalized equation, which then gives us Lipschitz continuity and single-valuedness of the solution. Another way to view these conditions is that if we take this second-order approximation of our optimization problem using the operator H as an approximation of our Hessian, and the Hessian is strongly regular, is positive semi-definite, then strong regularity is given if and only if these approximated optimization problem takes unique solutions under perturbations of both the equality constraints and the objective function, and the perturbation or the effect of these perturbations in equality constraints and objective function affect our primal-dual solution in some kind of Lipschitz continuous sense. Now, I've promised you we are going to look into the nonlinear programs, which are most often considered for this type of nonlinear optimization problems, especially when it comes to optimal control. Again, the assumptions here where we're looking at finite dimensional spaces, we have twice continuously Fouché differentiable objective function and constraint functions, and the constraint set, the feasible set, is effectively the non-negative orthant, or a combination of the Euclidean space with the non-negative orthant if you have only slack variables. Then classically in nonlinear programs, you get constraint qualifications. Mangasarian-Framowitz constraint qualification guarantees you that the dual variable exists at an optimal solution. Linear independence constraint qualification additionally guarantees you that the primal solution is unique. And then there's the concept of strong stability of a primal solution, primal stationary solution, so a primal solution which has a dual variable, which is given if under perturbations of your optimization problem, there is again a unique stationary solution of your perturbed problem, and also, as in the case of strong regularity, perturbations only have a certain bounded effect on the perturbed stationary solution. It can be shown, has been shown in the literature before, that if our necessary conditions are strongly regular, then in particular, the primal solution is strongly stable. It's a stationary solution because, of course, the necessary conditions have a primal-dual solution. And the Mangasarian-Framowitz constraint qualification holds at the primal solution with a unique dual. Uniqueness is a property of strong regularity, and the uniqueness of the dual actually implies MFCQ. Also, we have that the optimal solution is strongly stable if and only if MFCQ holds and we have a strong second-order sufficient condition. So we have local quadratic growth around our optimal solution. In particular, our optimal solution is a strict local minimum, so it's locally unique. And in reverse, if we have a strongly stable stationary solution, and in addition to MFCQ, actually LICQ holds, linear independence constraint qualification, then our necessary conditions are going to be strongly irregular. Now, these are fairly strong assumptions. And in the end, I'm going to comment briefly on possible relaxations. But now we want to study the system theoretical characterization. That's why we're here. We want to study input-to-state stability. And for that, we are looking at the somewhat reverse problem. Okay. Kind of missed this slide. I'm just going to skip it. Now, to study the reverse problem, we are introducing what I call a canonical perturbation, where the perturbation of our optimization problem just happens to affect exactly our value function, our objective function, and the equality constraints, pretty much in the sense as if we were studying strong regularity of the KKT conditions. In this case, the perturbation then becomes the right-hand side of the generalized equation, which is the KKT condition. That's kind of neat that we have the perturbation directly in a corresponding place in the generalized equation. And if we now assume that the generalized Newton's iteration, that we can postulate to solve the generalized equation, was locally input-to-state stable around the primal-dual solution, meaning we have the classical property of local input-to-state stability, and we have a stationary solution of our Newton's method, then we can actually take this inequality to the limit case because we have a stationary solution, and we get a Lipschitz type bound on the effect of a perturbation V on our fixed point and its distance to the unperturbed primal-dual solution. Now, any stationary solution or any fixed point to the Newton's method also is a solution of our perturbed generalized equation before we are doing the approximation for Newton's method. So we have equivalent to any fixed point of the Newton's method satisfies the inequality. Also, any primal-dual solution to our perturbed generalized inequality must satisfy this inequality by the assumption that we have local input-to-state stability. But now this inequality actually is the definition of our generalized equation being strongly suburregular at the primal-dual solution. Now, strong subregularity, as you could guess, is a relaxation of strong regularity where we have uniqueness of the unperturbed solution, but for small perturbations, the solution could be non-unique, still is bounded, but might not actually exist. So that's the kind of drawback from using this relaxation. We don't have guaranteed existence of a solution under perturbations. And most notably, if we relax the assumptions in our previous theorem to strong subregularity, we can still derive local input-to-state stability, but we lose the guaranteed existence of solutions to the Newton's method. So Newton's method actually might get infeasible or and otherwise don't have a solution anymore. But if it has a solution, it still is locally input to state stable. Now we can use the same approach of reworking what we need for certain system theoretical properties and look into an equivalent characterization of strong regularity, because I've told you ISS is actually necessary only for strong subregularity. So the question becomes, what do we get in addition if we assume strong regularity? And the answer to the question, what do we get in addition, apart from the guaranteed existence of solutions, is that we're actually having a type of local incremental ISS. So we don't have just ISS in the sense of perturbations from our nominal solution, but we get incremental ISS, which looks like a little bit like ISS and Lipschitz continuity combined. And this is necessary and sufficient for strong regularity of a fixed point under perturbations. Well, with that, we're nearing the end of my presentation. Just to summarize, regularity of the necessary KKT conditions play an important role in the sensitivity and stability of nonlinear optimization problems under perturbations. This has certain connections to stability of stationary solutions, but also second-order sufficiency conditions in nonlinear programs, possibly beyond. That's still a somewhat open question. And using strong regularity as this concept from variational analysis, instead of using these more classical notions such as strong second-order sufficiency or stable stationarity, allows us to discuss problems beyond nonlinear programs, which could include non-convex semi-definite optimization problems, nonlinear sum of squares problems. So basically everywhere where you don't have simple element-wise inequality constraints, or even infinite dimensional optimization problems, such as control optimization, optimal control problems on continuous time, for example. On the other hand, we've seen strong regularity is a fairly strong assumption, hence its name. And the strongness comes from the fact that it gives us uniqueness of an otherwise possibly non-unique optimal solution. And it actually gives us incremental ISS. That's how the strongness of the regularity assumption translates in system theoretical terms. We can relax these properties. We've seen that strong subregularity implies input to state stability, but we lose existence of the solutions to our Newton's method. Could also relax it to metric regularity if we have general nonlinear optimization problems. In that case, existence is guaranteed, but we lose uniqueness, and we particularly lose the property that any solution to our Newton's method, even a local one, would converge. We would only have guaranteed existence of a convergent solution under perturbations, but our Newton's method might actually evolve differently. And that's it. A couple of people who contributed to this work and are here briefly shown. With that, thank you very much for your attention. Very weird just speaking to my screen, to be honest. And I'm looking forward to a discussion where I'm hopefully seeing your faces again. Thanks.